So today we're going to be estimating the value of the natural log using an integral, and we'll see a few nice applications of that, and then we will go on and do a few more evaluating some integrals. So first we're going to define the natural log function by the natural log of x being the integral from 1 to x of the function 1 over t with dt. So another key thing in this section will be to use some properties of the natural log and some properties of exponents. So here's some properties. Don't forget, the natural log of 1 is 0. If I do the natural log of a times b, that's the natural log of a plus the natural log of b. If I'm dividing a and b, the natural log of a minus the natural log of b is the same thing. The natural log of any number to an exponent would be that exponent times the natural log of that number. The natural log of e is equal to 1. And then if we have y equals e to the x, the natural log of y equals the natural log of e to the x, which is just equal to x because the natural log of e is 1. E to the natural log of x is just x, same kind of deals from the last part. And then if I'm multiplying two numbers, I have to add their exponents when I put them together. If I divide two numbers, I subtract their exponents. And if I'm doing a power of a power, I multiply the exponents. We're going to use some of these when we do some derivatives in this section. Just go over a couple and show you how to simplify those. So the first thing is to express the natural log of 4 as an integral and then sketch the corresponding area. So our rule said the natural log of a number equals the integral of 1 to that number and then 1 over t, and we're differentiating with respect to t. So that means I need to sketch a graph of 1 over t, and I'm going between 1 and 4. So when I do 1 over t, 1 over 1 is 1, so that I'll just make that my highest number. So that's a point on my graph. 1 over 1 is 1. 1 over 2 is a half, so 0.5. 1 over 3 is 0.33. That's a little bit harder to do, so I'll do 1 over 4, which is 0.25. So that gives me a nice number there. I got my little curve, and I'm sketching the area underneath that curve between the x-axis, and I'm done. So here we're asked to use Simpson's rule with n equals 4 to estimate the natural log of 4. So we got to go back to our same definition that we had in the last example, where we go, it's the integral of 1 to 4 of 1 over t dt. So we're going to estimate this like we did before using Simpson's rule. So we need delta x, which is b minus a over n. So we're going to do 4 minus 1 over 4, because that's our number of rectangles, and then we get 3 over 4. So that means we need x naught being 1, and then we're going to do x1 being 1 plus 3/4, that's 7/4. x2 is 7/4 plus 3/4, so that's 10/4, which is also 5 over 2. x3 is going to be 13/4, and x4 is going to be 4. So with Simpson's rule, we pretty much have delta x divided by 3, and delta x divided by 3, and then we got the function at x0 plus 4 times the function at x1, 2 times the function at x2, 4 times the function at x3, and then the function at x4. So pretty much we are going to do 3/4 divided by 3 out front. My function at x0 would be 1 over 1. My function at x1 would be 1 over 7/4. My function at x2 would be 1 over 5/2. I've got 4 of my function at 1 over 13/4. And then I've got my function at 1 over 4. And we can clean this up a little bit. 3/4 divided by 3 is actually just 1/4. That's going to be 1. This is 4 times 1 divided by 7/4 is just the reciprocal of this 7/4. Same thing here. So I'm going to write this all out and then simplify a little further. Again, pretty much at this point, we're probably not going to leave our answer as a fraction anyway. So if you calculate this total, you should get 1.39162. If you type the natural log of 4 in, so the natural log of 4 is approximately this. On a calculator, if you type in natural log of 4, you get a little bit different. Now, if we went in being a lot higher, we would get closer and closer to this number. Another aspect of this section is to find some derivatives using the properties of logarithms to kind of simplify your expression. So here we've got a derivative of the natural log, and then we've got x to the 4th over x to the 5th plus 1. So when we evaluate this integral, we can actually split this up, or this derivative. I said the wrong word there. We can split this natural log up into the natural log of x to the 4th minus the natural log of x to the 5th plus 1. And that simplifies our derivative a little bit. This first part is 4 times the natural log of x. We can't really do that with the second part because of that plus 1. So we're going to have to do a little bit more work. So now we just have to do our derivative. So here we've got 4 times the derivative of the natural log of x. So we've got a product rule. However, the derivative of the 4 goes to 0. So we really just have 4 times the derivative of the natural log of x. So again, that would be 4 over x, because the derivative of the natural log is just 1 over x. And then we've got to do the chain rule here. So I've got 1 over the derivative. The derivative of the natural log is 1 over x plus 5, x to the 5th plus 1. And then I need the derivative of that x to the 5 plus 1 from our chain rule. So my derivative is equal to all this stuff. And I get 4 over x minus, and then the derivative of this part here is 5x to the 4th, so that goes on top of my fraction. And then I got x to the 5th plus 1, and that's my final answer. So we could get to an equivalent format not using properties of exponents and logarithms. However, this is a nice, way nicer looking way of getting this than doing all the other steps. We could have used the chain rule and then used the product rule a couple times, or the quotient rule, and gotten the same answer. It would have been ugly though. So we've also got some integrals here. Again, from the name of the section, they're going to involve the natural log. It's just some more substitution problem. So here we're going to have to use our substitution. So we need to recognize that the bottom is our u value here, x to the 4th plus 5, and then that du is equal to 4x cubed dx. Now when you're looking at this, you're like, okay, I have 3x cubed up here and I need a 4. So what number do I multiply 4 by to get a 3? 3/4 of 4x cubed on top of x to the 4th plus 5. This is going to be the exact same integral that we started with, except now, again, this is my du part, and the bottom is u. So I've got 3/4 integral of 1 over u du. Now we know how to do this integral because I've got 1 over something, and that means that's the natural log of the absolute value of u. And in this case, I don't have any upper and lower bounds, so I need a plus c. And then I just plug my u back in, and we'll have our final answer. So x to the 4th plus 5 plus c. That's our final answer. Again, same kind of idea here. We need to realize a couple things. Number one, I might not be able to do this just like it is, but I can split up a few things and that will help me. So I need to realize that this is just 1 over x squared, and then I've got e to the 2 over x dx. That will help me with my substitution. So if you look at this, u has to be that 2 to the x, 2 over x, the e to raise to that power, because if I do du, again, we can also write that as 2x to the negative 1. If I do du, I get negative 2x to the negative 2nd power dx, which is negative 2 over x squared dx. So if you look right here, I've got this nice part that's 1 over x squared dx, and then there's my du, so I can actually change that. However, I don't have just that. I've got this negative 2 with it, so in order to get rid of it, I need to redefine my integral as being having that negative 2. So in order to get rid of it and go back to my original function, I needed the negative 1/2 outside, and then I can make that negative 2 over x squared e to the 2 over x dx. And then here's my full du, and I can substitute. And I've got e to the u du, which we know how to do because the integral of that is just e to the u plus c, and then we just substitute our u value back in, and our final answer is negative 1/2 e to the negative 2 over x. It's just 2 over x, sorry, plus c. Alright, and here's my last example. Now you might be looking at this thinking, alright, I don't see anything I can substitute right now. And really, the first step of here is to realize I've got a fraction. I've got e to the 2x on the bottom, I got e to the x on the top. In this case, I'm going to have to just split this up. Alright, so I can take e to the x divided by e to the 2x, and then I can take negative 1 divided by e to the negative 2x and rewrite this integral. So I'm going to start by rewriting this integral. So I got the integral from 0 to 1, and then I've got e to the x over e to the 2x minus 1 over e to the 2x. I'll put parentheses there, dx. Alright, so really, e to the x over e to the 2x, again from our properties of exponents, is e to the negative x. And then, since this is a subtraction, we can go ahead and just split these up. And that's e to the negative 2x. So for this second part, I'm going to have to do a substitution. The first part we can go ahead and evaluate. But for this second part, I'm going to do a substitution. So u equals negative 2x, du is equal to negative 2 dx. So we're going to have to change this second part just a little bit. So I'm going to leave the first part alone first. Now, since I've got this negative 2, I need it in my integral. That means I need to change this and have a negative 2 here. That means I need a negative 1/2 out here. Alright, so I've got minus a negative 1/2. That ends up being plus 1/2, the integral from 0 to 1. And if I do that, I've got my u, I've got my du right here. So I've got e to the u du here. So the first part is really easy. Alright, I'm going to come up here with it now. My first part is e to the negative x, and I'm just evaluating that from 0 to 1. My second part is going to be plus 1/2, and then I've got e to the u. So e to the u would be just e to the u again, so I just put e to the negative 2x, and then I'm going from 0 to 1. So if I'm using the fundamental theorem of calculus here, I've got e to the negative 1 minus e to the... That should be a negative e. I'm sorry. I put that down wrong. That should be a negative e because that's e to the negative x. So I've got negative e to the negative x. So I got negative e to the negative 1. And then I got minus a negative, so plus e to the 0. Plus, and then I've got 1/2 of e to the negative 2 minus e to the 0. So we can simplify some of these things down. This is negative 1 over e. This is 1. This is 1 over 2e squared because I got e to the negative 2. And then 1/2 times negative 1 minus 1/2. And if I put the 1 and the 1/2 together, I get 1/2. And then I got minus 1 over e plus 1 over 2e squared is my final answer. So, again, just follow some step-by-step things. These are the same kind of integrals that we did before, just a little different. We use our properties of exponents and the properties of the logarithms to figure out our substitutions, simplify things down. So, just a little bit extra practice and another application of an integral really to be able to figure out the value of a natural log.